So the name of the game now is bonus malus systems. We'll be working with bonus malus systems. Now, this is the overview of the topic. This is a far more practical topic than the one we were working with in the last lesson, okay? Or, I mean, in the last slides, okay? So that now you know that. So first, we'll be working with the definition of the bonus malus systems, right? Then we will make a big stop, it's a rather big stop, in the Markovian analysis of the bonus malus systems. And then we will stop at taking a look at Loy-Maranta's efficiency. And yes, the proper way to say this is Loy-Maranta, okay? This name is due to the guy who discovered this. It was a Swedish mathematician, a Swedish actuary, actually. Okay, so now you know. So first of all, I need to tell you that practically every country in the world, just each country in the world has its own bonus malus system, okay? So the main feature between the bonus malus systems that a country and another country implement, right, is that they both can be analyzed from the perspective that we will be teaching during this topic, okay? So you can always take a look at this by means of using a Markovian analysis, okay? So insurers have introduced bonus malus systems in non-life insurance industry for two main reasons. First, to have, for instance, bad drivers, or that is customers who are just bad luck, to have them pay in the long run higher premium than good drivers or good clients. That is the clients that are like more lucky, right? And to introduce policyholders to drive more carefully. Now, in this case, as well as in the rest of the slides, I will just assume that we are in the context of automobile insurance, right? Now, it is absolutely not possible to implement a bonus malus system in an insurance of another kind. For instance, it is not possible to implement a bonus malus system in, for instance, life insurance. So say that we can implement a bonus malus system for a life insurance. Say we can do that. So how would you translate this into the language of life insurance? There is no such a thing as a good death. Yeah, so I mean, if you die, then you're no longer a customer for the insurance company. You see? So you die, and that's it. So they just pay you, and that's it. Okay? So it is absolutely not possible to implement a bonus malus system in a life insurance. Okay? However, it is possible to implement a bonus malus system in, for instance, still in non-life insurance, with, for instance, medical expenses, or for instance, I don't know, when you are insuring banks or some other financial entities. You see? Because in that case, what you have is just someone who is a good customer and someone who is a bad customer. Okay? However, the context in which this is just like really, really, really useful is precisely the context of automobile insurance. Okay? Okay, so in this case, we see the a bonus malus system for the Austrian country, for Austria. Okay? So in this case, we see the bonus categories, right? And the malus categories. So you have 1, 2, 3, up to 10 categories for good customers. So these guys end up paying less than these guys. Of course, it is absolutely necessary to enter the system. So how does a person enter the system? Well, they just enter at the middle stage, right? Where, for instance, they pay 100% of the premium, right? So they will be paying 100% of the premium, and after, for instance, 1 year or 2 years of experience, then the company decides if the person is going to be paying less, right? Or if they will get some other benefits, right? Of course, the most common benefit that the person can expect to attain when they enter a bonus malus system is to be paying less premium, okay? Okay, so here we have the main question of today's lesson. What do you think are the main a priori classification variables to differentiate premia among life insurance policyholders? Which one of these would you say are good a priori classification variables to differentiate premia among non-life insurance? So for the case of life insurance, age and gender are definitely the main classification, a priori classification variables. But for the case of non-life insurance of this, what would you say are good differentiators between the premium that a person pays and the premium that another person pays? So definitely car weight, definitely occupation, of course, gender. Now, when it comes to life insurance, I will use just green color, okay? So age, absolutely, gender, occupation, again, and marital status. Why is that? Because if you have, say, a married person buying insurance, then it will be very likely for this person to buy insurance for his wife or for her husband, you see? And of course, you can grant them a discount for the package, you see? So in here now, you can talk about the main classification variables to differentiate premium, okay? Now, you can see some variables that, I mean, I was a little bit hard on this because I said it's absolutely of no use, but actually you can use this, right? However, when it comes to deciding which are the best predictors, then you would definitely need to go for these ones. So if you have to choose a good predictor of what a non-life insurance is going to behave like, then you want to take this, okay? Because if you take, for instance, the past claims behavior, then this is absolutely the best way to know what the premium should be set to, okay? However, there is absolutely no way to have some experience if there is no information about the person, okay? Now, as for the car's weight, well, this is absolutely the best because of what I was telling you about heavy cars and the light cars. And of course, you can always check what is the distance between the home of a person and their work, right? So we just took a look at the advantages and at the disadvantages of implementing a bonus malus system, right? Okay, so here I give you 3 advantages and 3 disadvantages of setting a bonus malus system. So among the advantages, well, an advantage is that it avoids adverse selection. However, the economic stability is no longer guaranteed. Now, one of the advantages is that it promotes justice and balance. However, there is a principle, and this is just one of the main principles of insurance, the principle of mutualism. So just to transfer risk from one person to another, right? That principle is just broken when you set up a bonus malus system. You can assess better the individual risks. However, since you're using just a basis of what happens to a single individual, then the law of large numbers is not met. So in here, you have a really useful chart. So before you decide to implement a bonus malus system in a given population, just take a look at this, okay? So in here, I will just define, with all of the words, a bonus-malus system. So say that we have a population given by omega. And let us just have a finite partition of that population, right? A bonus-malus system is in effect if all three of these are met. First, we need to have a premium scale, right? And of course, S, little s, is just the number of elements in the partition, right? So we have one type of premium for each of the classes in our population, okay? Second, we need to have an initial distribution of the policyholders. So if you do not have an initial distribution of the policyholders, then you do not have a bonus-malus system, okay? And third, we need to implement a set of transition rules to go from one class to another. So when you talk about a bonus-malus system, you are inherently talking about a Markov chain, because you need to go from one class to another. And this, I mean, of course, it is the definition of the bonus-malus systems, right? However, this is also a definition of what? Of a Markov chain. You see? So whenever you want to state a Markov chain, you always need to state an initial distribution and a transition matrix, right? So you can characterize a Markov chain by doing this, okay? By stating first an initial distribution, and second, a matrix of probabilities of transition, okay? So that's just what a Markov chain is. That is why it is just so straightforward to use Markovian chains to describe bonus-malus systems, okay? In a particular bonus-malus system with three states, a customer pays premium C if he is in states 1 and 2, and premium A lower than C if he is in state 3. So please observe here that you will just charge less to the person who falls in state 3, okay? That says, to describe this system by a bonus-malus scale, notice first that there are two groups of drivers paying the high premium. The graph below models the transition between all three states. So this is also another way to represent a Markov chain. So you just have to display all the states in the chain, and then you just have to say what is the probability of going from one state to the other. And of course, the probability of going, for instance, from 1 to 2, from 1 to 1, and from 1 to 3, in this case, there is no way to go in a direct way from 1 to 3. Whenever you state these probabilities, then you need them to add up to 1. So 1/3 plus 2/3, that's 1. Now, let us check the case of the second class. We can go from 2 to 1. We can go from 2 to 3. And there is no way to return from 2 to 2 in just one step. But still, look at the fact that 1/2 plus 1/2, that's just 1. And that it's all the same with the third class, right? That is just the same with the third class, because the probability of going from 3 to 3 in just one step is of 1/3. Of going from 3 to 2 in just one step is of 1/3 again. And the probability of going from 3 to 1 in just one step is of 1/3. And last time I checked, 1/3 plus 1/3 plus 1/3, that was, well, equal to 1. Okay? So now I give you a definition which I took from books 1 and 6. This is just the definition of a Markov chain. So say that we have a finite or countably infinite set of states. A Markov chain is a sequence of random variables that satisfies the Markov property, and that is this thing here. So we can just have that the random variable indexed with number t plus 1 equals something given all this story? Well, if you are to meet Markov's property, then this conditional probability should equal just the probability that the same thing happens here, given that only the final part of the story happened. That means that whenever Markov property holds, all the story is erased. The only thing that matters is what happened up to this point here. So as you can see, a Markov chain, the Markov property, is just a way to generalize the memoryless property of a couple of random variables which you are very familiar with right now. Those are the exponential distribution and the geometric distribution. The first one in a continuous time scheme and the second one in a discrete time scheme. Okay? So a Markov chain is just a way to generalize that. However, in the context of stochastic processes, we cannot just let go all of the story, as happens with precisely those two random variables. We just let go this part of the story, okay? And you're supposed to just stick with this part here, okay? Now, this is a part which you should be very acquainted with right now, and this is just the transition matrix that corresponds to this diagram here. Of course, it is far simpler to just represent a Markov chain by, well, the transition matrix of a Markov chain by doing this table than doing this, right? So whenever we need to talk about bonus-malus systems, we will always take a look at this matrix of probabilities of transition. We just let Q equal the probability that xt, please observe that we're talking about the same t here, equals I for all the states in our classification. So this thing will just the probability distribution of on S for time t. Now, by the theorem of total probability, the probability to be in state J at time t plus 1 is given by this. Please observe also that this holds by the very definition of a marginal mass function, right? So whenever you see something like this, and this sum here, you should think of two things. The first one is the theorem of total probability. And the second one is about the way in which you compute marginal mass functions. This is just some of the material that you studied back then when you were studying probability 2. So in here we have class 1, class 1, class 2, class 3, and in here I have class 2 and class 3. So in here I have 2/3, and then I have 1/3, and then I have 0. Please observe that the sum from, if we take the sum in each row, we always get the 1, okay? So 1/2. Say that, we say that t goes from 0, 0, 1, 2, like this. Okay? And then we just take a few more steps into the future, right? And then, well, we talk about the probability of being in state 1. State 1, then we'll take the probability of being in state 2, and then we take the probability of being in state 3. Right? So just to begin with, I told you that we needed to have two things. First, the matrix of probabilities of transition, which I will paint in an AWACS orange. And of course, we also need to have an initial distribution. So say that the person starts at state 2. Okay? Now, according to this expression here, we need to compute this sum. But this sum is just, you can just obtain this sum by selecting this and then asking the spreadsheet to multiply what? This times all this. And then I just click Control, Shift, and Enter, and I end up having the distribution for what happens at time 1. Please observe that according to our table here, this is exactly what is supposed to happen. If you are at state 2, right? If you are at state 2, then the probability of going to state 1 is of 1/2, and the probability of going to state 3 is of 1/2. And this is exactly what happens here. Now, things begin to become interesting. So I'll just copy this here, and here, and here, and here. So what can you see, fellas? What do you see?
Convergence.
They're not changing. You see? So all I did was that I fixed the matrix of probabilities of transition, right? And then I just went one row at a time, all the way up to down to the bottom. You see? And eventually I get an invariant distribution. So what this means is that in the long run, I will just end up having 56% of the population in the first class, a quarter of the population in the second class, and the remainder in the third class. Now, what I have done here is really simple, because this is just an application of something which I expect you to be very familiar with right now. What we have done here is just to talk about a concept which you were already familiar with, and that was precisely the concept of invariant distribution, or the concept of invariant distribution. Okay? So thank you very much for your attendance, for your presence, and of course for your patience.